Okay, students, let's get ready with lecture or with our session for today. Get your clickers out and get your calculator out and get some scratch paper. We're going to be doing two ginormous point charge problems today that are going to help us understand covalent bonding in the hydrogen molecule H2. All right, before we get to that, however, I want to, we're going to do some clicking along the way, of course. And I want to go over the idea of quantum leaps in terms of the phase space diagrams. Just a reminder, a mental reminder to everyone here and to everyone that listens to this in YouTube, that we have a final exam on Friday morning at 7 a.m. and it is mandatory. It is also cumulative. So that means everything today is included and everything on Wednesday, at least for the first half of class. Second half of class, we'll probably have a little mini review for bonus points, a little study guide. All right. So I can't overemphasize the importance of being here at 7 a.m. sharp. I will be here, and my two TAs, my GTA and my learning assistant, Kendra, is going to be here with bells on. All right. And be prepared because it is going to be difficult. And even I don't say that to be mean, but you probably realize this from your, everybody's in here sat through many finals, tough science classes. Even if I made all the questions multiple choice and easy, because it is cumulative, it would still be challenging to remember concepts from August. I mean, it's December now. This is December 2nd. Uh-oh. That says session 30, November 4th. I'll change that before I YouTube it. This is the 40th session, December 2nd. And so you got to, remember all the way back. And that alone is going to make it, even if I made all the questions easy, going all the way back in the Wayback Machine memory-wise to remember those concepts and stuff would definitely be challenging. So also, I've been seeing people coming down with bringing Chick-fil-A right in front of me. See, this is, and they're smiling. Anyways, I've been seeing people coming down with nasty viruses and stuff. And the key thing is to get sleep. Do not stay up. Rachel, do not stay up all night. Don't do it. See, she's coughing as soon as I said it. So I you guys are all experienced, so I'm just nagging you a little bit, but because I want you to do well in the final. And by the way, I'll just add this since it's pretty much the last week of class. It has been a lot of fun for me having you guys and teaching you guys. Now, we've been through some difficulties, and I've had to yell at a few people, not the least of which the people that bring Chick-fil-A in right in front. No, I'm just kidding. But it's been fun, and even for those of you that I have yelled at a time or two, and I'm not looking at anybody, but I don't hold a grudge. I hope everybody here does well in the final. All right, because I really want to see that. And if you earn an A on the final, if you crush the final, and you get your grade all the way up to an A, baby, you got it. There's no curve in here. You earn it, you got it. All right. So let's keep going. I want to talk about this idea of quantum leap that I ended lecture with on Friday. No. last Monday, a week ago. Boy, it was a nice week off, wasn't it? Oh, we need more of those. We talked about this phase space diagram. This is for a simple spring mass system. It's a little rough. This is the sketch I had. Um, it's also in the YouTube. And we talked about, the energy levels of each one, the smaller one having a smaller energy level, and the fact that you measure the area of each ellipse, any ellipse, or any other area. I mean, it doesn't have to be a perfect ellipse, in units of angular momentum or in the advanced categories, action. And I told you that quantization of energy levels. We were talking about standing waves, and that standing waves was de Broglie's way of explaining um, electron orbitals. In other words, that they're quantized, and they're quantized because he saw them as standing waves, and standing waves only exist at certain radii because of certain energies. All right. And I'm going to show you a slightly different way of looking at quantization here. Um, and my comment is simply that for using phase space like this, I mean, it's pretty complicated. There's a lot of fancy mathematics behind this, but the diagram itself is easy to explain in terms of a spring system, and it does allow you to drag out some interesting analytical features. Okay, so for instance, now I'm going to give you a real light. Now, nobody goes around doing research on springs anymore. Engineers probably do it for a living somewhere in a spring company, but here's something that's right out of the pages of the New York Times, so to speak. This is electrocardiology. This is a phase space, what they call a phase space reconstruction of the uh, electrocardiogram for a patient with sinus rhythm. Okay. Now, sinus rhythm is the normal bump, 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 bump. It's not an arrhythmia, so it's not like atrial fibrillation. We have a different, fast, slow, fast, slow. It's just not, and you can see the trace of the electrocardiogram traces out. It's not an ellipse, but it's pretty regular. It's following basically the same path. All right. And here's the reference if you care to look that up. It's in the International Journal of Cardiology from 2015, March of 2015. So this is pretty good. Here's the page. And so what they're trying to use is the phase space reconstruction to make a prompt and accurate diagnosis of ventricular arrhythmias. All right. Now, why do they want to make it prompt and accurate? Well, they don't want people dying, is basically the theory on that. Because if you look down here in the abstract, it says accurate and timely diagnosis of ventricular tachycardia. Okay, that is death. That is sudden cardiac death. All right. So if you go into God forbid that you experience ventricular tachycardia, that's bang, you're done in a few seconds. Same thing with ventricular fibrillation. Now, atrial fibrillation is a little different. But these two, especially ventricular fibrillation, that's not a heart attack. That's what we call cardiac arrest, sudden cardiac death. And that's why we have all these these portable electric defibrillators out in the hallway and stuff, here and there around the building. So here's some phase space reconstructions in black and white. Okay, so figure A up here, let me get my cursor over here. Up here in the upper left, figure A, that's a sinus rhythm, kind of like the one we just looked at. Now this one's a sinus rhythm with a VPB. Now I think that's some, do you know what that is? Does anybody know what VPB is? I forgot to look it up. It's some kind of venous, I don't know, or valve problem. But it's not, but you can see it's very close to a regular sinus rhythm. Now down here in C, That's ventricular. That's a mess. The phase space reconstruction for that baby is an MESS. That's ventricular tachycardia. And option D is even worse. Ventricular fibrillation. That thing is all over the place. We wouldn't even call that chaotic, but it's definitely doom, for somebody that has that. Unless you can blast the heart out of, fibrillation. That's what, like if you're watching some TV show, in the emergency room, and Arnold Schwarzenegger puts the two things on the guy's chest, and then somebody says clear, and then they hit a button and he gets jabbed with, or he gets blazed with, a bunch of joules of electrostatic energy. Yeah, that's what you want to do. That'll save somebody from ventricular fibrillation, hopefully. So these phase-space constructions, you can analyze them, and we do the same thing in quantum theory. One of the nice things about it is you can tell the direction of time, or you can represent the arrow of time in a phase-space diagram, which is kind of cool. All right. You can also, have different energy states and so forth, different springs. So in other words, a different spring might look way different. So I put a bunch of different ovals here, or ellipses, big and tall, small, wide, so those phase space representations are important. Now, here's another one, another system, guitar strings. If you go and buy some Diodario nylon classical half-step trebles, you just look up the specs. All right, they have a tension specification in the booklet. All right, there it is. All right, they just have a list of them in the booklet, and so every string has a different one. Every string has a different unit weight, pounds per linear inch. All right, and unfortunately, this is using the English system, but that's all right. It's good because guitars are great. The scale length, the distance from the guitar's nut to its bridge, which we talked about last time, it's different sizes. So a classical guitar is about 25.5 inches, 100 centimeters. But a mandolin, what did I say? 20, that's not right. 100 centimeters, 60 something centimeters. The mandolin is only 13.875 inches. All right, so what that means, so you're talking different ellipses, and each of them has, because they're different lengths, they have different tension, and they have different scale length and weights. They have different pitches if you're on key. All right, there's a tuner on the back of a Gibson that's built in, I guess. It's kind of nice. I see the serial number there on the Gibson. All right, so now each pixel of each string has its own phase space ellipse. All right, because the way that you model a guitar string, it's an oscillating system. It produces waves, but physically you consider every pixel to be oscillating vertically up and down at a certain frequency, and all that's controlled by the tension, the weight and the thickness of the string, and all that stuff. All right. And so different strings and even different strumming styles will lead to different ellipses in phase space. Now, this guitar is very nice. Okay. Spring and a mass, very nice. Here's why we care about it. Here's a system that we talked about last time. There's the de Broglie relation, lambda equals h over mv. All right. And we talked about the different energy levels. So that's different kinds. You can think of every energy level as being a different string on a guitar. All right. They have different energies, different wavelengths, and different frequencies. All right. And therefore, you can represent them, it turns out, as ellipses in phase space. And what a quantum leap is the system leaping between two different ellipses. from a high, if you go from a bigger ellipse to a smaller ellipse, as in it, you guys aren't even looking at this diagram. My God, this is everything. This is visual 100%. You jump from the big one to the small one, that's like dropping an energy level because the small one has a lower energy. All right, now we can think of springs that way, but it turns out that you can talk about atoms the same way, like the hydrogen atom. In fact, this was one of the earliest ways of understanding quantization of energy levels in a hydrogen or hydrogen-like atom. Okay, so the area is measured in kilogram meters squared per second. That's angular momentum, or as we say in the business, action. And here's the rule. You know, de Broglie said you have to have standing waves. Okay, nice. But then when somebody figured out, all right, what are the standing waves going to look like in phase space? What kind of ellipse will they have? This is the rule, that you get constructive interference when you change the area, the cross-hatched area, in multiples of Planck's constant. If you do that, you'll always have constructive interference and a quantum state. You'll have an acceptable energy level. All right, now that's for any oscillating quantum system. Now it gets really, this is very, very basic, but that's a very simple way of looking at quantum systems. Jumping ellipses under the proviso that the new area is only one H or maybe two H's or maybe three H's smaller. There's some number of Planck's constant. And for that reason, I always say that Planck's constant is the one constant to rule them all. It is the one that makes atoms behave the way they behave. So everything that you have in electronics, the sun, the nuclear reactions in the sun that give us sunlight and warmth here on Earth, the polar structure of water molecules is all related to H and jumping those ellipses. All right, so that's quantum leap. Let me pause for questions. Cassandra. Go ahead.
You said that the constructive interference only happens when it goes, does it have to only be downrange with that?
Well, it will only emit a photon when it's going down. If it absorbs a photon, it'll jump to a higher ellipse. And it's a certain energy only. And it corresponds, when you analyze it ellipse-wise, 1H above, 1H more area, 2H's more area, 3H's more area. It's very precise.
So the energy levels is like H, 2H.
No, the energy levels are not H. H is the quantum of action. And remember, the phase space is an abstract representation, but you can count from the phase space diagram. You can calculate the energy. You know, it's one half for a spring system. It's 1/2 K times maximum extension squared, X max. Okay, so you can get it. It doesn't show the energy, but you can calculate energy off, you know, however wide your, or, you know, maximum momentum. That's the top and bottom. You know, it's 1/2 times 1/m times P max quantity squared. That's your upper and bottom. So the diagram will allow you to calculate the energies, but the diagram itself, yeah, it only exists in chunks of H. All right. You know, those are the only ones that are. So you can't have like you can't have like 2.705 H between your ellipses. If you try that, the other one won't have a standing wave. You know, so if you want to drop 2.705 H, fine, but it's not gonna be to an energy level for which there's a standing wave. Okay, so it's kind of cool how it works. Now I want to go back to our standing wave discussion. Here's an image of Andrew, and those hands in the right or no, on the left side are Brad. He's not in the picture, but he's a critical part of this whole discussion. There he is. Okay, so, and those guys over there are the observers. Cassandra and all you guys over there at that table, looking so thrilled and interested. And let me just point out to you that if you go into the PSC 1121, the wider area, not our playlist, but the wider area for PSC 1121, you'll see an entire playlist for wave demonstrations like this. This one's from a few years ago. Those are two of my TAs, my undergraduate TAs from, years going by, and they both they both have masters now, and they're both very successful. All my TAs do really good. Did you know that, Andrew? Yeah, Kendra's going to do good. I don't know about you. All right, so here's some data from our waves. Now, I want to talk about the idea of containment or confinement for a wave system. And we had a containment size. It was basically Andrew's and Brad's feet, 2.66, which Rachel Dupuy measured. Wait a minute. Is that right? Is that your name? Rachel? Right? Rachel Dupuy. Yeah, I thought I had it right. Now she measured 2.66, so that was good. And we all measured the period, came out to about 0.642 plus or minus 0.0006. That's pretty good. That's like 0.1%. And then that corresponds to a frequency of about 1.56 hertz. Now, next time I do this, I'm going to make the two guys stand a little bit further apart. Wavelength 5.32. This is for the fundamental mode, and the speed 8.29. Now, I want to point out some concepts for you, but let's do a multiple choice question first. Turn on your clicker and just hit the refresh key once. We're going to do multiple choice. And this one, you got to read. Read very carefully. So this is about confinement or containment. If you confine the distance between endpoints of a slinky to 2.66 meters, as we did in session 39, then the set of standing wave resonances have this property or set of properties. So choose one of those, think carefully, and make a choice. Can you guys count, please? Nice. Think carefully. The final exam. How about if I, this is the kind of thing, you guys are going to med school. You'll get multiple choice exams, Scantron, where you have questions like this. "30 seconds. Okay, good. You put that in. Of course, it's good. Very good. "10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. All right. Now let me show you what we got. Houston, we got to do some splaining here. All right, we got a little bit of controversy here. It's all right. We can handle it. All right. So let's talk about this. This the standing wave. The standing wave has to fit uh, at least one bump between the two containment points, between the endpoints. Then the next one is a bump and a dip. Then the next one is a bump, a dip, and another bump. And then that's the second excited state. And the third excited state is 2 bumps and 2 dips. So you're always going up by some simple fraction of 2.66. So 1 is good, all right? Roman numeral 2, frequency and wavelength are set at specific values and no other values produce standing waves. That is correct. You know, it took Andrew a couple seconds to get the frequency right. That's what he controls, the frequency. He controls how often he jiggles the spring. And that is what controls everything. But certain frequencies, he didn't quite have it right. But when he got it right, you could see it. Right? So 2 is good. Number 3, frequency can be anything, the wavelength is fixed. That is false. If the reason that that's false is on a spring or any kind of oscillating medium, usually there's a set wave propagation speed. So it's V equals lambda F. So if you change the frequency, you have to also change the wavelength because the wave speed is the same. Okay, they're inversely proportional. So 3 is out. What about 4? There's a specific resonance that is the lowest frequency and no resonance exists below that frequency. That's correct. You can't get anything more than our fundamental. That's why we call it the fundamental. In atomic physics, you'd call it the ground state. All right, so the answer here is C. And let's see what you guys voted for. Yeah, a plurality of people voted for C. But, you know, go ahead and add those to your notes if you haven't already. And 1, 2, and 4. Now we're going to talk about some more things about the coil spring system, and they're actually going to correlate to some quantum physics concepts that we need. And actually, we've already talked about it on Monday last week. All right. And I'm going to go to the next one. If you haven't got all this jotted down, you can jot it down from YouTube a little bit later. Now, the coil spring containment. Andrew's end, you know, he's out there basically generating waves. Okay, the waves. But when a wave comes back from Brad, it reflects back. It bounces back from Andrew's hand. So it's all reflection, and there's no absorption. Well, theoretically, there's no absorption. I mean, his hand does absorb a little bit of energy, but for the most part, we consider it to be no absorption. All right, so that means that his hand is perfectly rigid like a wall. It reflects everything, it absorbs zip. Okay, so it's like an impenetrable wall. All right, perfect rigidity. So it's not made of jello. It's not made of silly putty. It's not made of plywood. Plywood you can get through. It's not perfectly rigid. Uh, Now, the same thing with Brad. He's got the same situation, except the waves are coming in from the direction of Andrew. So he has perfect rigidity like a wall, and he wasn't even doing anything for the most part. I mean, you could feel it trying to jiggle your hand, all right. Yeah. So he's got the same situation, perfect rigidity like a wall. So this makes the system like a one-dimensional box of size D. So that's why I put this picture of a truck. Okay, there's the first excited state from front to back of the truck. Um, and the dimension, basically the size of the length of the cargo box there, particle in a box, is controls everything. All right. So how does that apply to an atom or molecule or a quantum wave? So, when we're talking about an atom or molecule, that's our main topic for today. And actually, we're going to talk about molecules and molecular bonding and stuff. Those aren't springs down there. Those are quantum waves. So that's a different kind of a critter. But we're still going to be looking for this idea of containment or some kind of bounding left and right, or bounding inside at small radial distance and outside at larger radial distance from the nucleus or wherever it's floating around. All right. So all that standing wave demonstration that we talked our ears off about was for that reason. All right. So let's talk about bonding. All right. Okay. So what we're going to do is a classical model of a hydrogen molecule, H2. All right. So a couple protons. Let me get this banner out of the way here. Okay. And I'm going to give you coordinates. So label carefully. Here's an electron. And distance unit is 1 nanometer. And here are the positions: -6 nanometers, comma 0, -2 nanometers, comma 0, +2 nanometers, comma 0, 2 nanometers, comma -3 nanometers for that other electron. All right, so go ahead and jot and make a good picture. We're going to do, and you're going to have to maybe do another couple of versions of this because we're going to do calculations out the wazoo with this. All right, so prepare to have your brain challenged, possibly even burned up to a crackly crisp, a crispy critter state. All right. So this is you could, Professor Rutherford in 100 years ago, 105 years ago might have thought, well, yeah, this could be a hydrogen molecule, proton and an electron, and they're bound together, or at least they're in this picture they're near each other, a couple of nanometers away. So go ahead and clear your calculator, hit the refresh key. And this one I want a letter, and I've got, let's see, I've got 10 options. All right, so this has to be alphanumeric. So put in the letter that you want. All right, don't try to type the answer and just type in A, B, C, D, E, F, G, H, I, or J for this one. All right, so back to the diagram. How many interacting pairs are there? All right, let me get this. Look at your diagram, do some sketching. And I guarantee you this is going to cause you to think. Because remember, the Coulomb interaction is a pairwise interaction. At the fundamental level, it's an electron interacting with another electron, or an electron interacting with a proton, or a proton interacting with another proton. So take a minute to think. Yeah, look at that. Look at that diagram. Hey, would you guys like to have some office hours today after class over my office? Anybody want to come? Rashid Haroon, office hours today after class. 15 seconds starting right now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Um, let me take a look at what you guys answered. Oh my goodness. Let's take a look here. All right, so here's my setup. All right, and let's just map it out. So eyeballs, check it out. Here's the first pair. Okay, proton, a red strand. We're just doing some bookkeeping here, visual bookkeeping. All right, and then, all right, here's the purple dotted line. It's purple because it's going from between blue and red. All right, so that's two. And then here's another purple one down here, blue and red, proton to electron. So that's three pairs. You know, so when you're trying to figure out the forces on any one of these particles, you got to think of all the other pairs. So if you're trying to figure out the force or the electric field on proton B, you got to figure out these pairs. Then here's this one. That's another purple dashed line from proton. Oh, by the way, label your protons A and B the way I have them, just for bookkeeping. And we'll call the electrons number 1 and number 2 the way I've got them. Just jot that down. All right, so this is proton A to electron number 1. Now we also have electron to electron, so that's a blue curve over here. So that's 5, right? Okay, so the answer is 5, right? What? You dare to challenge the great Dr. B? Oh, so it's 4 then. So I shouldn't have that one.
It's
6?
2 to B.
Oh, wait a minute now. Daniel Sierra. What have I forgot? Oh, you mean this? Dun, 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 yeah. So 6 is your answer here. And if you didn't answer 6, a few of you didn't, go ahead and jot down this little diagram here or make a note of it. You know, maybe over to the side. Now, this is really nice. Connect the dots. Very lovely. Very, good. Kindergartners like doing this too. Everybody likes connecting dots. But the reason that we're doing this, we've been talking about energy levels, quantized energy levels. You can, there's all kinds of things that can be quantized, like angular momentum, but we're concentrating on energy levels. So what we want to do is try to calculate the potential energy V of the entire system. So now here are the 6 potential energy terms that you've got to calculate. All right. So the potential energy of the AB interaction, proton to proton. The potential energy of proton A and proton or an electron number 2. Potential energy of the, it's basically KQ1 Q2 over R. So it's not like a bodacious calculation. So proton B to electron 1, proton A to electron 1, and then V12, that's electron to electron, and then VB2, that's the last one that we drew in, from proton B all the way over to electron 2. Question, Daniel? That's right. It's the sum of the energies. And the nice thing about this, you guys, no trig. Well, there's a little bit of trick. You got to figure out your radii. Because the formula is basically, here's V12, for instance, KQ1, Q2 over R squared, or over R12. You don't have to square it. It's just the radial distance. Okay, now this will give you uh, the potential energy for that part of the system. All right, you got 5 others to do. All right, and notice that your numerators are all going to be KE squared, but also notice that Q1 and Q2 for electrons 1 and electron 2, that's minus E and minus E. So it comes out to a positive KE over R12, or KE squared over R12, positive. But now your purple ones, proton to electron, are going to have a negative sign because it's an E times a minus E in the numerator. Now K, you guys are going to have to calculate this in a second here. So this is your example, and they're all going to be like this. You're going to have to use 9 times 10 to the 9 Newton meters squared per Coulomb squared. You know, by golly and by gosh, I finally have mesmerized Coulomb's constant. I think I got it, even the units. All right, so we're going to calculate this. Now we're going to start with a Cinci calculation. All right, so this next one is going to be numeric. And sorry, I don't have hit the refresh key, but go to numeric, hit your refresh key, and do this calculation. Very cinchy. Calculate R12. You got to do that for every pair. And some of the pairs are pretty easy, but so you guys can go ahead and circulate. And let me stand up. Ugh. Oh man, my back. So give me something point something something nanometers, and then hit your send key. Anybody over there have a straight edge? Nobody has a straight edge? No, they're too big. I gotta draw something up here. Is there a protractor over there somewhere? With toast. That's all right. I'll do it by hand. That's all right, guys. Work on your calculation. 1 minute. All you gotta do is calculate a distance. It's not rocket science. Not this part. 1 minute. How are they doing?
Good. I mean, they're all making it way too difficult.
Yeah, it sounds like it. Okay. 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. 8.539. Look at this. Majority of people voted for this. So I don't know. Let's see what. Now here's your line segment right there. All right. So it's just a hypotenuse, and the horizontal part is from -6 to +2, so that's 8, and it's 3 down, so that's 3 over here. So 8 squared plus 3 squared is 64 plus 9, 73, and so yes, 8.544. So 8.54 is what you should. And I'll give. Yeah, I think that it's got one of those. Let me over here. So I'll call this good. It's a computer glitch there. These ones you have an order of, yeah, a factor of 10. This one too. This one's all right. Actually, what did I say? Point something something nanometers. So this one's, yeah. So this one, oh, so this one's not right. Wait a minute. No, that one is right. These other ones, yeah, these other ones are not right. Okay. Not to two, yeah, not to. Well, um, you guys, when you're doing this, one of the things that you can do is factor out a factor of 10 to the minus 9 and just park it outside all your calculations. Because if you square, for instance, 3 times 10 to the minus 9 meters, that's going to be 9 times 10 to the minus 18, right? And if you square 8 times 10 to the minus 9 meters, that's going to be 64 times 10 to the minus 18. Now, they both have a factor of 10 to the minus 18. So you add up the 64 and the 9, you get 73. So your big square root is the square root of 74 or 73 times 10 to the minus 18 meters, square meters, inside the square root. So when when you do that, it's the square root of 73 and the square root of 10 to the minus 18, which is 10 to the minus 9. So square root of 73 nanometers or 8.544 is kosher. And and the reason that that works nicely on this is because, especially on these potential energies, the denominator is just r. It's not r squared, so you'd have to worry about it too much down there. Yeah, sure there was, because the oh, I see what you're saying. Uh, well, this is the right answer, anyways. 8.544 times 10. Yeah. So right. So you square root 10 to the minus 18 square meters, and you get 10 to the minus 9 meters. And then you say, okay, that's a nanometer. So you're still left with square root 73 times a nanometer. So it just factors out. All right, Cassandra.
You weren't asking for the radius?
The radial distance, R12, the distance from 1 to 2, that's what R12 means. Okay? So it's always a Pythagorean theorem problem. To get R, unless unless the two, like proton A and electron 2, they're right, they're sideways, so that's an easy one. You don't have to do Pythagorean theorem for that. But some of the other ones you do. So, all right. And in fact, I can see another one where you have to do some Pythagorean theorem. RA1, you're going to need to do Pythagorean theorem carefully for that. Now, why do I want you to do RA1? Because eventually you're going to calculate the total energy. But before we do that, let's do a subcalculation. All right, here we go. Numeric problem. And I want your answer in joules times 10 to the minus. So drop the 10 to the minus 20. You're gonna get something in the order of 10 to the minus 19, 10 to the minus 20, 10 to the minus 21, somewhere in there. All right, so factor that out and just give me three significant figures. All right, now this is VAB. All right, so that's proton to proton. Go ahead and calculate that. And it's KQ1, Q2 over R. In this case, RAB. And you're going to do another 5 of these for the total one, but let's get this one squared away first.
For the K, didn't we use 8.99 or 9?
For K, use 9 times 10 to the 9 Newton meters squared per Coulomb squared. 10 to the minus 9. But you don't have to square that or anything. It's just r in the denominators. Yeah, it's 4 times 10 to the minus 9 meters. Because K and Q are in meters and newtons and stuff. So yeah, 9 times 10 to the 9 for K, and it's Newton meters squared per Coulomb squared. Thomas? Well, I didn't. I was going to try to look at some more of the solutions, but I couldn't get it to. I couldn't get that cursor or that pull bar to pull down. No, I know it's the processor. It's a computer error. There's certain numbers that will always go in like that. Yeah, it's just because of using binary math.
For the Q, do you want us to use 6.02 or 6.023? Because it's
For Q,
yeah.
1.602. 1.602 times 10 to the minus 19 coulombs for the electron and the positive for the two proton charges. No wonder you're off. See, this is a good little review set.
Okay.
3 minutes starting now. Two minutes. 'Hey, don't put in E minus 20. I told you, don't do that. Just give me the mantissa. Something point something something.
Yeah.
30 seconds. Seven, six, 5, 4, 3, 2, 1, 0. Okay, let's take a look at the results here. Yeah, you guys are geniuses. 5.77, and I don't think we need to. Actually, yeah, let's definitely check this, double check it on document cam. Can you swap me over to document cam? We'll just do this real quick. And double check your notation here. That's on freeze. All right. So this is the interaction here that we're trying to calculate the potential energy. So V is equal to K Q1 Q2 over R 1 2. All right, so that's K E squared over, oh, sorry, this should be RAB, RAB, okay. And so Q1 and Q2 are E and E, so this is K E squared over here. And then the distance is 4 times 10 to the minus 9 meters. Okay, so this is pretty cinchy. So 9 times 10 to the 9 Newton meters squared per Coulomb squared in the numerator. And also 1.602 times 10 to the minus 19 coulombs quantity squared divided by 4 times 10 to the minus 9 meters. Okay, now this is going to come out in Newton meters because Coulomb squareds cancel and one of the units of meters cancels. So I'm going to get joules out of this. And this is 2.56, I think, something over here. This is 4, so you know it works out to this is 10 to the minus 38, so this is 10 to the minus 29 on top, 10 to the minus 9 on the bottom. Let me look at my figures. I calculated this already once. So you've got 9 times 2.566, 4 times 10 to the minus 20 on top. And then it's joules, and then divided by 4. So that works out to 5.7744 times 10 to the minus 20. Okay, so for this, we would type in 5.77 for the answer. All right, so that's a cinchy one. Now what we're going to do next, you guys, listen carefully. We're going to do all the other 5 interaction pairs, and be aware that electron to proton, those are going to have a minus sign in them. All right, so you got to handle your minus signs as well. Now this one, proton to proton, that was all positive. And this one over here, 1 to 2, that's going to be negative to negative. That's also going to be positive. All right, but the purple ones, electron to proton, there's 4 of them. You're going to have minus signs. So do that carefully. All right, and so and I'm going to give you a good fraction of time here to do this. So here's your next question. Now calculate the total potential energy. Same thing in terms of 10 to the minus 20 joules. All right. So this is for everything. All right. And so just crank it out. And if you need a minus sign, make sure to use it. Go ahead and circulate. Hey Andrew, do you know how to use Instagram? Do you know what does the infinity sign mean? Do you know?
I think that's for like videos.
It is?
Yeah,
Well, it's too certain. No, that's an infinity sign. Anyways, I just was wondering what it was. I'm getting pretty good at this Instagram business. Yeah, well, I don't have any cool filters. Just not a. It's just diagrams and stuff. But notice how quiet it is. Everybody's thinking.
Professor Brown told me if I could come and grab something from the
Hmm. Yeah. What do you got? Some circuitry stuff, or?
It's some lasers and
Oh, very
I guess
nice.
some reflective surfaces.
Cool. Nice. Nobody's typed in an answer yet. That's all right.
It's all set.
Kendra, how they doing? They getting there?
Our R's formula, she flashed me back to when I had her class.
Oh, yeah. Key equations. See, we already did this.
I mean, all the problems she gave us,
We did
always had
this.
to integrate. Always had to integrate.
Really?
Yeah, she'd give us a formula and she'd be like, okay, but it's for like a different shape in a different area. Integrate the new formula. I'm like, oh. Yeah, it was with calculus, so she wanted us to use calculus.
Yeah. What was that? 2049? Yeah. 2048. Most people haven't had a full semester of calculus because they take Calc 1 and 2048 at the same time.
They should require Calc 3 before 2049
You
because
th-
it's dot
yeah,
products and everything.
I
But they
know.
don't. And I'm pretty sure there's a triple integral in there, but they don't
I
require
did a
it.
triple integral in 2048 once.
Really.
Oh my goodness. That was instant, and it was in the big lecture hall downstairs. So 300 students, insurrection. I thought I was going to get, strung up or something like that, or run out of town, you know. But I calmed them down. I said, "Oh, it's just another integral."
Triple integrals aren't that hard.
They look hard.
Because there's many curves. Because
Yeah,
when in Calc 2, like, you learn the hardest part of integrals, but the thing for triple integrals is they make it easy in polar coordinates tables. So it's like the
yeah.
simplest one.
So if they're independent, then they just multiply through independent coordinates. So, well, these guys have had 10 minutes. 3 minutes. Move it. Gabrielle Souffrant. Get your answer yet? Hurry up. 2.5 minutes. check these answers. Thirty seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4. Timeout. Hurry up. Jenna, you got it? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Now let me see what the answers were. Huh? Negative 1.64. Nobody got even close to that. Let's take a look. Let's take a look. Here we go. Go to swap it out. All right. Shh, 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 shh. Quiet now. Shh, 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 shh. Let's just go through. Let's do another one here. I'm not going to talk over you guys. All right. So the first one is 5.77. So that's this guy over here. Let's do this one. Okay. That's minus. So that's VA1. Okay. So that's minus. Let's see. This stuff up here is going to be the same for all of them. Okay. So that's, what is that equal to? 20 something. 2.3098. So this is 2.3098 times 10 to the minus 10 to the minus 20. Let's just double check that. Okay, here we go. 9, enter exponent, 9 times 1.602, enter exponent negative 19 times 1.602, enter exponent negative 19, 2.3098 times 10 to the minus 28, and that's Newton meters squared, divided by, okay, now this distance is 4. 4 times 10 to the minus 9 meters. Okay, so that's equal to divided by 4, enter exponent negative 9, 5.77. Yeah, okay, that's the same size except it's negatory. Negative 5 point. So look at that. Times 10 to the minus 20 joules. Okay, so that's the same calculation as we had up here. All right. All right, because this pair, A and 1 are 4 nanometers apart, and so are A and B. Now, B and 2 are 3 units apart, so let's do that one. Okay, so B2 is negative, and that's the purple, 2.3098 times 10 to the minus 28 Newton meters squared divided by, okay, 3 times 10 to the minus 9. That's 28 meters. All right, so let's go 2.309 8, enter exponent negative 28 divided by 4, enter exponent negative 9. All right, so what? Oh yeah, okay, so that's wrong. Let me do that again. Let me clear that again. I'm used to doing fields. 2.3098, enter exponent negative 28 divided by 3, enter exponent negative 9. Okay, so that's negative 7.6, negative 7.70 times 10 to the minus 20 joules. Okay, so these two, the first VA1 and VAB cancel, but I still have this one. So this is a minus 7.70. All right, now I got 3 more to go. I got, let's do V12. V12 is negative 2. No, that's positive 2.3098, 2.3098 times 10 to the minus 28 Newton meters squared. Now this one's the 8.54 times 10 to the minus 9 meters. That's the square root of 73. That's this one here, from 1 to 2. That's this baby. All right. So that's positive. So let's see, 2.3098, enter exponent, negative 28 divided by 8.54, enter exponent, oops, do that again, 2.3098, enter exponent, negative 28 divided by 8.54, enter exponent, negative 9. Okay, so this is 2.7, and it's positive. 2.70 times 10 to the minus 20. Okay, so now that, so I'm going, I'm going up against a negative here, so this is 2.70 over here. All right, so let's do VA2. All right, so that's this baby. Now I already know that's a 3, 4, 5 triangle. All right, so I already know what that one is. VA2 is negative 2.308, 3098 times 10 minus 28 Newton meters squared divided by 5 times 10 to the minus 9 meters. All right, let's check that one out. Okay, 2.3098, enter exponent, negative 28 divided by 5, enter exponent, negative 9. Okay, so this is 4.62, and it's negative, times 10 to the minus 20. So that's a negative 4.62. All right, so now I've got 5. What's my last one? VB1. All right, so here's my last one. VB1 is also easy because that's 8 units apart. So negative 2.3098 times 10 to the minus 28 Newton meters squared. This is good. I'm double checking my own work here. So this is 8. See, because I did all this on a spreadsheet, but it's good to do it by hand sometimes. All right, so 8 nanometers. All right, so let's try it again here. Clear. 2.3098, enter exponent, negative 28 divided by 8, enter exponent, minus 9. Okay, and that's also negative. You know, I think my answer is wrong. There's unanimous agreement. So let me. So this is 2.89. This is negative. So I should have 4 negatives here. Times 10 to the minus 20. So that's negative 2.89. Now VA2, is that what this is? Yeah, this should be negative here. Oh, it is? Okay. Oh, yeah, okay, this is V12. V12. Okay, so that should be positive. Okay, so I've got, okay, so there's these 3. All right, so I'll ignore these 2 up here because they already cancel out. So I just have to calculate these ones. So let's see, 0, 0, 2, 1, carry the 1, 2, 9, 15, 23, carry the 2. Uh-oh, that's no good. I can't do that because some of them are positive. All right, let me just do them up. Okay, so here we go. Negative 7.1 plus positive 2.7 minus 4.62 minus 2.89. Uh-oh, anybody get 11.9? This is 7.7. Yeah, okay. Let me do this again. Negative 7.7 plus, now this one's positive, 2.7 minus 4.62 minus 2.29. I still get 11.9 negative. 11.9 negative. Well, let's look at the answer. Let's look at your guys' data. Let's take a look at it. Go ahead, switch me over. See now, now take a look at this. A lot of you guys voted for negative 12 point something, 12.5. And that's close to what I have. So I'm going to have to double check my figures. And you know what? You know what we're going to do? I guess I'll give you a homework assignment because we're running out of time here. All right. Here's what I'm going to do. My wonderful students. What I'm going to do is double check my figures, and I'm going to give if you're right, negative 12.5, and I am wrong, I'll give double points to everybody that answered that. So I'll figure out some way to do that. Hold on. Hold on. But if I'm right, should I subtract double points? All right, so now you got 12.5? Yeah. Negative 12.5. All right, I'll double check. I have it on my, oh, I have it on my spreadsheet. So what I'm going to do is check my spreadsheet. So what we're going to do we're going to dismiss, but before we do, I'll have office hours today, 12:30 to 1:30, over in my office because we didn't have any last week. So, all right, and I think what I'll do is I'll set up a single homework problem to do the next calculation because this one, we got to get this one right. When we get this one right, I'll grade it and everything. But the whole point of this is to make a variation in the position of the protons and then recalculate. And the reason, now I know I got that right in my spreadsheet. Now, you know what I might have been looking at? I know what I might have looked at the wrong. Yeah, I might have got seriously, so I miscalculated something there. Yeah. I think I know what I did. I looked at the wrong column in my spreadsheet. So the hydrogen molecule, H2, they're bound. But the problem with the binding is the protons are positive. They should repel, right? And the electrons, they're floating around. There are these quantum waves orbiting the protons. The protons are just kind of sitting there. So how is it that those two protons bind together? Because of the influence of the electrons, all right? And that is what, and so the second calculation that I'm going to set up for homework tonight, due on Wednesday, is going to introduce us to covalent bonding on Wednesday, and we'll finish the semester with that, all right? So it'll be a single calculation, and I'll make double sure that did I get it right? I do everything right. Because when you're doing a spreadsheet, if you put one plus sign or a comma wrong somewhere, it screws everything up. So, but I know I know I got that potential energy curve, so that thing's looking sweet. But I'll do that. So homework tonight, one problem due on Wednesday, and office hours at 12:30. You're dismissed. Let me see that. I think, you know what I was doing? I think I was doing it in electron volts. No, for the answer that was in the slides. Yeah. Let's see. So, let me get my cursor over here.